All right, let's talk about ChatGPT. We've all seen the incredible, sometimes weird things it can do. But how on earth does this thing actually work? Today, we're going to pull back the curtain and step by step build one conceptually from the ground up. You've gotta love this. It can be a poet, a coder, or a hilariously overdramatic news anchor for a falling leaf. The results often feel like actual magic, don't they? But it's not. At its core, it's just a language model that is incredibly good at one thing, completing a sequence. The real question is, how did it get so good at, well, just finishing our sentences? Believe it or not, this is really all a large language model is. It's a system that's been trained to do one thing: predict what comes next. You give it some text, and its entire job is to calculate the most probable next word or character or even just a piece of a word, what we call a token. It's basically the world's most powerful text completion engine. Okay, to understand something this complex, we have to start simple. Really simple. So we're going to build our own tiny language model, and we're going to train it on a pretty small data set, the complete works of Shakespeare. Our only goal is to predict the very next character in a piece of text. First things first, a neural network doesn't read letters. It only understands numbers. So our very first step is called tokenization. We just take the raw text, find every single unique character to create our vocabulary, and then we swap each character for a corresponding number. That's it. We now have a long sequence of integers, which is the language the machine actually speaks. All right, let's start with the most basic model you can imagine: a bigram model. To predict the next character, all this model does is look at the one single character that came right before it. So if it sees the letter T, it's learned from all of Shakespeare's work that H is a really common letter to come next. It's super simple, but you can probably already spot the massive flaw, right? Yep, exactly. A memory of one character is basically no memory at all. This model has no idea about words or sentences or plot or anything. It's just playing a game of single-letter dominoes. To write anything that actually makes sense, a model needs context. It needs to remember what happened earlier in the text. And this is the breakthrough. The whole game changed in 2017 with a paper called "Attention is All You Need." It introduced a revolutionary idea called self-attention. This is the secret sauce. It's the mechanism that lets the model look back at all the previous words and decide for itself which ones are important for predicting the next one. So how does this self-attention even work? The best analogy is to think of it like a conversation happening between all the words. Every single word, or token, produces three little signals: a query, which is like it asking, "Hey, what am I looking for?" A key, which is another word answering, "Hey, here's the kind of information I have." And a value, which says, "Okay, if our query and key are a good match, here's the actual information I'm going to share with you." And here's why that is so brilliant. Before this, models would just kind of mush all the past information together into a simple average, and a lot of detail got lost. But self-attention creates a weighted average. Through that little conversation of queries and keys, the model figures out exactly which past words are most relevant for the current word. It can now literally pay attention to important context, even if it was pages and pages ago. Okay, so we've got this incredibly powerful idea of self-attention. What do we do with it? Well, we package it into a neat, standardized, repeatable unit. Think of it like a Lego brick. This is called a transformer block. It's the fundamental building block of GPT, and just like Legos, we can stack them on top of each other to build something really tall and powerful. But hey, why have just one of these conversations happening at a time? The next big upgrade is called multi-head attention. This lets the model run a whole bunch of these self-attention processes, all at the same time, in parallel. Each head can learn to focus on something different. So you might have one head tracking grammatical rules, another keeping an eye on the plot, and a third tracking who's talking to whom. It creates a much richer understanding of the text. So inside every single one of these transformer blocks, a simple two-step dance happens over and over. First, the tokens communicate. They use that multi-head attention to talk to each other and gather all the context they need. Then, second, they compute. Each token takes all the information it just gathered and thinks about it for a bit on its own using a standard neural network. So it's communicate, then think, all the way up the stack. Now, when you start stacking dozens and dozens of these blocks, networks can get really hard to train. So there are two clever engineering tricks that make it all work. First, something called residual connections, which act like an information superhighway, letting the training signal take a shortcut and flow easily from the top of the network all the way to the bottom. Second, layer normalization, which basically just recalibrates the numbers after each step to make sure they don't spiral out of control. It keeps the whole training process nice and stable. So we have our blueprint now, a stack of transformer blocks that communicate and then compute. The magic of models like ChatGPT really comes from what happens when you take this architecture and you just scale it up to an almost unimaginable size. So, just how big are we talking here? Just look at these numbers for a second. It's staggering. Our little Shakespeare model, which is already pretty complex, has about 10 million tunable knobs or parameters. The largest version of GPT-3 has 175 times billion. We're using 6 layers of those blocks. It uses 96. And the data? Forget 1 million characters of Shakespeare. We're talking 300 billion tokens from a massive snapshot of the internet. When you see it visually, it's almost absurd. The bar for our model is barely even visible next to the absolute skyscraper that is GPT-3. And this immense scale isn't just about making it a little better. It actually leads to brand new emergent abilities, things like reasoning and translation, that just don't exist in the smaller model. Okay, so we've built this massive raw language model. It's a phenomenal text completer, but it's not yet the helpful assistant we know as ChatGPT. There's one final, absolutely crucial stage that turns this raw engine into a useful tool we can actually talk to. You can really think of the whole process in 2 main steps. First is the pre-training phase. This is the incredibly long and expensive part. And then there's a much shorter, but just as critical, second phase called fine-tuning, which is also known as alignment. The pre-training stage is everything we've been talking about. The model is shown that huge chunk of the internet for thousands of hours with one simple goal: guess the next word. In the process of doing that, it learns grammar, it absorbs facts about the world, it even starts to develop basic reasoning skills. You end up with an incredibly powerful document completer. But a document completer isn't an assistant. If you ask it, what's the capital of France, it might just complete it with another question like, what's the population of Spain? The fine-tuning stage fixes this. The model is then trained on a much smaller, curated dataset of high-quality questions and answers, all rated by humans. This is what teaches the model the pattern of being a helpful, instruction-following assistant. So when you see a number like this, 175 billion, you now know what it really represents. It's not some unknowable black box. It's the result of these core ideas: tokenization, self-attention, transformer blocks, and just massive, massive scale, all followed by that careful process of fine-tuning to align it with what we humans actually want. And that leaves us with a final, kind of fascinating thought. This whole process is just about finding and replicating patterns in data. But when a system is trained on a dataset as vast as the internet, a dataset holding a huge slice of human knowledge and communication, what subtle underlying patterns might it discover about our world, our logic, and maybe even ourselves that we've never been able to see? It's a powerful question to consider. Thanks for joining me for this explainer.